Now let's look at some estimation examples with graphs. So we see graphs all the time. Magazines, newspapers, websites often display information using circle, bar, or line graphs. They're great because they're really visual. People tend to like them, right? They help us understand the data a little bit easier. So the following examples illustrate how rounding and other estimation techniques can be applied to data displayed in each of these types of graphs. Sometimes what I do, if there's a lot of pictures or a lot of heavy definitions, I will just copy them right from the book. So this picture was just taken right from your textbook, and you can find the original in your e-text. Circle graphs, also called pie charts, which are, this is an example here, show how a whole quantity is divided into parts. Circles are divided into pieces or sectors. So each of these different pieces is called a sector. And what happens is the whole thing together is a whole. So you do want to keep in mind that when you have some sort of circle graph, that the total should be 100%. You may see very slight rounding error. Like if you got 99.9%, it could just be that some of your percents were rounded, but it should be 100%. It should not be more than 100% or less than 100%. If that's the case, then a circle graph is not for you. So circle graphs are only used when you break down a whole. So the total should be 100%. If you're doing other calculations, there's different graphs that we can use. Percents are the result of expressing numbers as parts of 100. So think about that word cent. We have cents in a dollar. There are 100 cents in $1. A century is 100 years. That word cent means 100. So percents are out of 100. So for an example, we see that there's a 41% here. Define old age as a decline in physical ability. So that's one way that they see old age is like you can't physically do things anymore. So that 41% represents a value of 41 out of 100. And that's how you can convert to a fraction. So if you need to go from a percent to a fraction, we just put it over 100. To convert a number from a percent to a decimal, what you're going to do is move the decimal point 2 places to the left. So that 41, now if you don't see a decimal point, it's always on the right. So you move that 2 spots over, and that's how you get that 0.41. In either case, technically, you're dividing by 100. So if you're stuck and you're like, I don't remember how to do this, to go from a percent back to a number, so percent to a number, either a fraction or a decimal, you're just dividing it by 100. Now, there are lots of applications that involve percents. So the basic formula looks like this. That word of means multiplication. So you typically take the percent of something. So whatever you're taking the percent of, that's what you're going to multiply it with, and that gives you the amount. According to the U.S. Census Bureau, in 2016, there were, 219,345,624 Americans 25 years and older. Assuming the circle graph in the previous figure is representative of this group, answer the following questions, right? So we're going to use the circle graph here. Use the appropriate information displayed by the graph to determine a calculation that shows the number of Americans 25 years and older, so that's who are in this group, who define old age by a decline in physical activity. Okay. So we saw up here that 41% believe that really represents old age, that decline in physical activity. So our percent here is that 41%. Now our base here is who it represents. So that 41% are these Americans 25 plus, right? And there are this many. So there are 219 million of them. So to get our calculation here, we take our percent, that 41%, and we're going to multiply it by this 219 million. Now, you can't just use percent, you have to convert that over. So you can either use 41 over 100, make sure to put it in parentheses in your calculator, or you're going to convert this over to the decimal form, which is what most people do, and use 0.41. So when I do that, take that 0.41 and times by 219, 345, 2, try this again, 219, 3, 4, 5, and then it should be 6, 2, 4. And what I get here is 899,31705.84. So that's going to be your exact answer. Now, I know you have a decimal. You can't have a fraction of a person, but what happens with these percents is they were likely rounded. So they probably took the values first, and instead of using a percent that was like 40.9% or 41.1%, they rounded it. So that's why you're a little bit off here. So really, it's probably 899,31706 because that 8 would bump that 5 up. So that would be your exact answer. But we can use rounding to find a reasonable estimate instead. So for instance, that 41% is really close to 40%, right? So what I could do is round this to the nearest 10. That 1 would drop it down. So instead I can use 40%, which is 0.4 or 40 in my calculation. Now, my base is still that group of Americans, but this number is so messy. I'm going to round this, and I'm going to round this to the nearest 10 million. So I'm going to take that 1 and underline right here. And then I'm going to look at that next number, that 9. So that 9 is going to bump that 1 up to 2. So I'm going to use 22, and then I have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7 zeros. And when I multiply them together, what happens is I get about 88 million. And that's close to here. Again, it's not exact. It is a little bit off, right? That 40% rounding down really does make a big difference here. So 1% of, 200 million people actually is quite a lot of people, right? So we do have a little bit of discrepancy, but it's a close estimate. So you can see that quite a lot of people, feel this way. Now, there are other types of graphs, not just circle graphs or pie charts. So we have bar graphs too. Bar graphs can go vertical like this, or they can even go horizontally with the bars going left to right. So this is a vertical one. Bar graphs are convenient for comparing some measurable attributes of various items. The bars may be either horizontal or vertical. Their heights and lengths are used to show the amounts of different items. So they tend to be frequency amounts. So how many are in each group? So here's an example. And the graph shows the life expectancy for American men and American women born in various years from 1950 through 2020. So your females are in yellow and your males are in red. Again, this was just copied right out of your text so that I could talk about it a little bit easier with you guys today. So for instance, a female who was born in 1950 is expected to live to around 71.1 years old, whereas a female born in 2020 is expected to live to 81.9 years old, so almost 10 years longer. Use the data for men to estimate each of the following. So again, we're estimating here. A man's increased life expectancy rounded to the nearest hundredth of a year for each subsequent birth year. So first of all, we're focusing just on the men, right? So we're looking at the change. So how life expectancy is increasing. So we're not looking for the exact years. We're looking for how are those years changing, because we can see that they're going up over time. Now, there's a few ways you can do this. So one way is you can kind of go year by year, but that's quite tedious. Another way is to really use the idea, if you've seen it before, of slope or average rate of change. So what slope says is that we can take two values. So we can take our y values, which are our heights here, and then we can subtract them with our x values in this case, which would be the horizontal. So these would be the years. Now, if you haven't seen this notation yet, don't worry too much. You don't really need to know the term of slope or average rate of change. I'm bringing it in here because some of you may have seen it before in an algebra class, so it really relates. So here, I'm going to take the first one and the last one. So I'm going to compare 77.1 and 65.6, and that correlates to 2020 and 1950. So this lets me look at the change overall instead of just going like year to year to year, one at a time. That can be pretty tedious, and then to try to figure out a pattern. So we're going to look at the overall change, the largest to the smallest year, and then in this case, it's the largest height to the smallest height as well. So we're going to use a calculator. Let me take my calculator out. All right, so I have 77.1 minus 65.6, 11.5, and then I have 2020 minus 1950, which is 70. And when I divide this, I get about 0.16428, and so on. Now it asked me to round to the nearest hundredth. So I'm rounding to the nearest hundredth, which is that place right there. My next value is 4, which is small. So it's going to keep that 16 the same. So about 0.16 is the answer. So for each subsequent birth year, a man's life expectancy is increasing by approximately 0.116 of a year. So 0.116 years. Okay, now this is still an estimate. Now you're probably saying, yeah, but there's so many decimals going on and stuff like that. But the reason it's an estimate is because we're taking just 2 points. We're looking at 2020 and 1950, and we're just kind of finding the average change that happened overall. So it may not be exact from year to year, right? So it could be a little bit different. Some years may have bigger jumps, other years less small jumps, but we're taking an average. So that's what makes it really kind of not exact, but more of an estimate. So for part B, the life expectancy of a man born in 2030. Well, let's see. I know here that in 2020, his life expectancy is 77.1 years. I also know that we're increasing by 0.16 for each additional year. So if we're going to 2030, this is a change of 10 years, right? 2020 to 2030 is 10 years. So what I can do there is use that idea to kind of find that change. And this is just one way to do it. So 10 years times 0.16 is going to give us 1.6. So 77.1 plus 1.6 is going to give us about 78.7. So this is the way that I would do it. I would think more about that change, but you don't have to do it that way. Another way to do it is, and this is how your book does it, is they started with the year 1950. So they said, well, in 1950, a man's life expectancy was 65.5, and now we're going to 2030. Well, this is a change of 80 years. So 80 years times 0.16, that's going to be a different number, right? That's going to be 12.8. So when we add 65.6 and 12.8, we actually get a little bit different answer. We get 78.4. Okay, so again, we're estimating here. So people can estimate in different ways. This is how your book does it. They use that starting value of 1950, whereas I use the ending value of 2020. But either way, you're looking at about 78.5 years is going to be that life expectancy there. All right, and let's do one more graphing example, and then we'll talk about models. So we can also use line graphs. So line graphs basically is really a scatter plot, so kind of individual points that we connect with lines, little line segments. So they're often used to illustrate, trends over time. So our bar graphs tend to be counts, like how many in each category. Lines tend to be used for trends over time. They could be months, years, etc. They frequently appear on the horizontal axis. So usually you tend to see time is on the horizontal axis. And then the amounts are generally listed on the vertical axis. So actually a similar idea to bar graphs. Points are drawn to represent the given information. So remember, just like a regular graph that you've learned about already, this is your x-axis, this is your y-axis. So each of these would be points, that x comma y point. And the graph here on the left shows the average age at which women in the United States married for the first time in 1890 through 2015. So you can see in 1890, they tend to marry around the age of 22. In 1920, it dropped to almost 21. And then 1940 went up a little bit. And then around 1950 here, it dropped again to almost 20. So there was a decrease in the average age. Now, or closer to now, out in 2015, the average age of a first marriage was 27. So we can see how things have changed over time. You will see a little squiggle here. So sometimes if we cut out information on a axis, we will use that little squiggle to say, yes, we're skipping numbers, right? Because we don't want it to count from 0 to 20 if there's really no data underneath there. So we skip numbers. We should never do that with a bar graph though. And that's because bar graphs, so this example here, you should never skip numbers on the axis because those heights of a bar graph actually have a correlation with the area and how large they are as a rectangle. So if you skip numbers, then the area of your rectangle is off. That's not the same with a line graph. So it's okay to do that as long as you note it. And we do it quite often. So like I said, you can kind of look through the different points. We can see in 1980 that the average age of when a woman married first was 22 years old. So we can kind of match up those values and find the point. So let's look at an example here. Using a line graph. So we're going to use this line graph right here. The line graph in the figure shows the percentage of U.S. college students who smoked cigarettes from 1982 through 2014. So first thing we're going to do is find an estimate for the percent of college students who smoked in 2010. So let's look at our tick marks here. It looks like they're going by 4. So I have 1990 and then it jumps to 1998. So this tick mark must be halfway between. So 1994. Again here, this one should be another 4 years. So 2002. So this one looks like it would be 2010. So if I'm looking for 2010, I'm going to go right up here and find out that point. And if I follow it to the left, kind of looks like it's right in between there. Again, this is an estimate, right? So you can't really be 100% sure because the graph is kind of small. But I would say that it's probably around 18%. Right, it looks to be about halfway between 16 and 20. In which 4-year period did the percentage of college students who smoked cigarettes decrease at the greatest rate? So let's talk about that. When your graph is decreasing, you see a downward trend. We read graphs from left to right. So when you're decreasing, your graph kind of goes down like this. When you're increasing, your graph goes up like this. And if you remember slope, you have like a negative slope versus a positive slope. You don't need to know that here, but just kind of thinking back to some algebra. Now, at the greatest rate is when it's going to be the steepest. Okay, so the rate is speed, right? So how fast is it decreasing? So you want to figure out where is the greatest decrease. So you're looking at that slant. Where is it the steepest? So I'm looking for decreasing trends. So these are kind of slowly decreasing. Here it's increasing. And then here I start to see some really good decreases. So I'm trying to figure out which segment looks to be the steepest. And again, it's an estimation, but it looks like this segment here tends to be the steepest, right? It kind of looks the most steep, the most vertical. So I would say that is the steepest. So this is the steepest segment for decreasing. So for B, it would be from about, let's see, that is 2002 through 2006. And then finally, in which year did 30% of college students smoke cigarettes? So we're looking for 30%. So 30%, if I look here, is about here. So I follow it across to see if I can get a match. And it looks like it matches right there. So I would then match it going down. If I follow that down, I'm looking at 1998 about. So I would say the answer here would be about 1990. Okay. So when we use our graphs, remember we're matching. So each of these points has two coordinates. It has an x coordinate from the horizontal axis, and it has a y coordinate, so like a height from the y axis. That one point gives you two values. It gives you, in this case, the percent, so the height, and then also correlates to the year on the horizontal axis.